All right, let's take a look. Let's see what we got. So we have HCN. What would HCN be called? What's the CN ion? What's that? Cyanide. And what do we do with ides? We turn them into acids? So like HCl is what kind of acid? HCl? It's not sulfuric acid.
Hydrochloric.
Hydrochloric. So ides turn into hydroics. So cyanide would turn into hydrocyanic acid because ides turn into hydroics. Okay. Okay. So HCN is going to react with H2O. It's an acid, so we're going to get H3O plus CN minus. Right? Hopefully you all got that. All right. So I don't know why you would put that on there. I never use it. Okay, so we start with 0.25. We don't start with any of these. Minus x, right? So 4.9 times 10 to the minus 10th equals x squared over 0.25 minus x. Let's try to drop that out. So, I don't know, what do we get for x? Something times 10 to the minus 5th? 1.106. And that's equal to my H3O plus, so my pH is almost 5. 4.9 maybe? 495?
Yeah.
Okay. Now hopefully by now that's becoming real easy for you. We've done this like, what, this is the 5th or 6th time we've done this, right? So you should be feeling pretty comfortable with that, and I think the homework that was due today had a bunch of these on there too, so hopefully you got extra practice. All right. So let's extend this a little bit. So this would be part B, so everything's still the same. But now, I don't just have HCN, I added some potassium cyanide to it. What's the pH now? After I add some potassium cyanide.
It's the same.
Oh, is it, you're adding product, right?
Now, there's one piece of data that probably you should know, but which it's been a while since we talked about it, so let me remind you again. What's the difference between strong and weak in chemistry?
Whether it
Completely breaks up or not, right? Okay. Anything that is attached to column 1 is a strong electrolyte. What does that mean? What would a strong electrolyte mean?
Completely dissolved.
It completely breaks up. It doesn't mean it dissolves infinitely. It just means that anything that dissolves is completely broken up.
Yeah.
Okay? So potassium cyanide. Is it a strong or weak electrolyte?
Strong electrolyte.
Strong electrolyte, which means it totally breaks up. Do you have a question? Yeah. Yes. It's this problem, but now I just added some KCN too. That's what's happening. So when KCN breaks up, what's it going to break up into? When potassium cyanide breaks up, what's it going to break up into?
Potassium and cyanide.
It breaks up into its name, right? So it's going to break up into potassium and cyanide. Does the potassium change the equilibrium on that equation over there?
No.
No.
It's not
No, because potassium's not in that equation. How about the cyanide?
Yes.
Yes.
Ooh, which way is it going to shift the reaction?
To the reactant.
Can you see I've added cyanide? It's going to go that way, right? Cool. This
That's so cool.
is called a common ion. Whenever you get two reactions and they share a common ion, then their equilibriums influence one another. So the HCN would theoretically influence this equilibrium also, except which one's stronger? The strong, and so therefore we ignore the weak, right? So we don't have to worry about it influencing that equilibrium. Yeah, let's see what the pH is at.
That's so cool.
So I guess it'd be
Yes. They're just maps.
I just tried plugging in instead of 0%.
So what changed over here?
The starting CN.
That number right there changed. It went from 0 to 0.15.
Yeah.
Everything else is exactly the same. So 4.9 times 10 to the minus 10th equals x times x plus 0.15 over x minus 0.25 minus x. Okay? Well, let's do like we did before. If x is really small relative to what?
0.15.
Yeah, we want to be really small relative to the smaller one so we can drop them both. Then in that case, both of those will drop out.
And it is.
And at that point, it should be pretty easy to solve for x.
It's actually
I don't know what it is, but like 8 times 10 to the minus 10th, something like that? 9?
8.2 times 10 to the negative 10. Oh,
So what's my pH now?
86. 9.09.
Okay. See how it works. So if you add a common ion to this, you're going to change the pH. Right?
Yeah.
What if I do this? Let's just set 0.15 molar of each of those. What would the pH be? Got 0.15 molar salt, I got 0.15 molar HCl. I mix them together. Right? And I've got my okay. Do I have a common ion?
Yeah.
So I start with 0.15. I start with 0.15. I start with 0. How much HCl breaks up?
All of it.
Yeah, it's a strong acid. Well, hold it, I thought Cl was going to shift the equilibrium towards reactants. What's the K for HCl?
Infinite.
It's infinity. So I shift the reaction to reactants. But I'm still working with an infinity here, right? It doesn't matter. So, yeah. So in this case, I don't have a K, right? And so it doesn't matter.
Yeah.
My pH would be whatever that guy is. Right? Anytime you see a strong acid, it doesn't matter whether you put a common ion in there. It doesn't matter because the K is so large that any shift you make isn't going to make any difference.
Yeah.
Okay? Just don't worry about it. So anytime you see a strong acid, you go, what's the molarity of the strong acid? And you say, okay, that's my pH. Whatever my molarity of strong acid is, that's how much H I've got. Find the pH directly. You don't have to put it in an equation. You don't have to do any ice tables. You don't do anything. You just go, strong acid. 0.1 molar strong acid. What do I put? I put 12 molar salt in there. Whoop-de-doo. I don't care. It's still 0.1 molar strong acid. So negative log of 0.1. Okay? All right. Let's go back to HCN. Okay. Now that has a K of 4.9 times 10 to the minus 10th. What does that say about the bond? Oh, well, first off, is it primarily reactant or product? With a K of 4.9 times 10 to the minus 10th.
Primarily reactant.
It's mostly reactants, right? Because K is products over reactants, and products over reactants is 10 to the minus 10th, which means my products are really small relative to my reactants, right?
Yeah.
Just basic algebra, right? Okay, so my reactants are really small, which means that when it reacts with water, water is not really able to pull that molecule apart. It's a very rare water molecule that has enough energy to be able to get in there and slam it apart and knock them apart. Do you see that?
Mm-hmm.
What does that say then about the strength of the bond between H and Cn?
Strong.
Do you see that it would have to be pretty strong?
Yeah.
Because here you got this pretty strong bond between H and Cn, and then boom, you've got water hitting it, and the HCN bond is going, so what? Hit me all you want, I'm not breaking up. On the other hand, what about the HCl bond?
It's very weak.
Can you see how it would have to be really weak? Because basically any water molecule, no matter how wimpy the water molecule, goes in there and goes, and breaks it apart.
Yeah.
Okay? Doesn't matter. Right? So notice what you've got here. The strength of the acid. How does the strength of the acid relate to the strength of the bond between H and whatever else is next?
It's inverse.
You see how they're backwards? They're inverse. The weaker the bond, the more it's going to break up. The weaker the bond, the stronger the acid is going to be. And those guys that I mentioned, the 6 strong acids, are the ones that have such weak bonds that there basically isn't a water molecule out there that can hit them, that can't hit them and break them apart. They can pretty much all break them apart. Whereas this HCN is a really strong bond, and it's the pretty rare water molecule that can actually break them apart.
Yeah.
So the stronger bond, the weaker the acid. Okay. And obviously, back and forth, stronger bond, weaker bond, stronger. So H and CN really want to be next to it. They really want to be bonded together. So what about CN minus? What does it want to do? First off, from the equation, what does it want to do? CN minus. In the HCN equation over there, what does CN minus want to do? You see it wants to gain a hydrogen, right?
Yeah.
So it really doesn't want to get rid of the hydrogen, but if you manage to get rid of it, it really wants it back. Because it's going to form a nice strong bond if only we could get them back together again. And so you run into this issue all the time. If it really wants to give up a hydrogen, then the conjugate base really doesn't want the hydrogen back because it really wanted to get rid of it in the first place. If on the other hand, if it really didn't want to give up a hydrogen, then it totally wants to get back in there and grab one, the first one it can find, to get back to what it wants to be. Right? And so there is an inverse relationship between the strength of this and the strength of this. So if this bond is really strong, this bond is really, well, if this bond is really strong, then this has, so not much of this breaks up. This is really going to be out there trying to gain a hydrogen. And compounds that really want to gain hydrogens, what do we call those? A compound that wants to gain a hydrogen.
Base.
It's a base, right? Bronsted-Lowry base. And so if it's a weak acid, the conjugate base is stronger. Let's take a look at that. So here's my conjugate base. And now I'm going to react it with water to go back to HCN and OH minus. Right? So this is a Ka, this is a Kb. What if I add these together? HCN plus Cn minus plus 2H2O goes to HCN plus Cn minus plus H3O plus OH minus. Can I simplify that?
Yeah.
And get rid of these HCNs on both sides. I get rid of Cn on both sides. Oh my gosh, look what I have left.
It's just water.
That's water. This is Kw. And do you remember when we add reactions together, we multiply the equilibrium constant? So Ka, Kb equals Kw. Let's do that with, let's take the negative log of both sides. So pKw is equal to log AB is what? Log A plus log B?
Yeah.
So pKw is equal to pKa plus pKb, and pKw is 14. So, somebody want to take the negative log of K, that 4.9 times 10 to the minus 10, tell me what that is. What is that? It's like 9.5 or something? 10.5? I don't know. Whatever it is. Negative log of 4.9 times to the minus 10.
9.3.
9.3. Okay. So my pKa so what's my pKb?
14 minus 7.
So my pKb has to be 4.7 because the two have to add up to be 14, right? Look how much stronger that cyanide ion is as a base than HCN is as an acid.
Yeah.
You see how it's a lot stronger? It's got a much higher pK, the pKb is much higher than pKa, right?
Yeah.
All right. So if you have, well, let's take it to the extreme. What about Cl minus? What would the pKb of Cl minus be?
0.
pKa is infinity, right? So the pKb would be 0. Right?
Give or take.
1 over infinity? It's just
Yeah.
essentially 0, right? So, whenever you are, so the Cl ion, because it's the conjugate base of a strong acid, has no influence on pH. And as a matter of fact, if you take salt water and you measure the pH of salt water, it's still 7. Because the Cl didn't have any effect on the pH. So no matter how much salt I put in that water, I did not change the pH because it's the conjugate base of a strong acid. What if I went down to the store and got some iodized salt? So now I added some potassium iodide. What's that going to do to the pH? How about iodine?
Raise.
That's the conjugate base of another strong acid, HI.
HI. So
HI, HBr, HCl, right? So I added potassium. Oh, but hold it. What about potassium hydroxide? What's that? What kind of base is that?
strong. base.
Strong or weak?
Strong.
Strong, because it's called 1, right? So K plus is the conjugate acid of a strong base. What's its effect on pH going to be? Strong means you can't measure the K,
Yeah.
right?
Yes.
1 over unmeasurable is as close to 0 as we can get, right? It's not, so whether it was a strong acid or a strong base, the conjugates aren't going to do anything because as the acid gets stronger, the base gets weaker.
Yeah.
As the base gets stronger, the acid gets weaker. Because the two together have to balance out. The two together have to be Kw. Right? So if we go stronger acid, right? Really weak acids have really strong bases.
Yeah.
Really weak bases, really strong acids. They're backwards. Right?
Yeah.
All right. Well, that can lead us to an interesting place. What if I don't have an acid or base in my solution at all? Here is a well-known fact. Copper sulfate. You guys have all used copper sulfate, right? It's that blue solution. It's acidic.
Yeah.
It tests as an acid. Well, where's the stinking acid? I don't see acid in there.
Isn't it conjugate?
Is it a conjugate? It is conjugate. So let me show you a quick and dirty way of figuring out how to tell. Once again, this is a Symcox method, so be warned, okay? Ask yourself what acid and base would make this compound. So what acid, what base would make this compound? So what acid would make this compound?
H2SO4.
I would make sulfuric acid, right? Okay, and what base would I use to make this compound?
Copper sulfate.
Does that help?
Copper
So what base? How do we make a base? What do we add to something to make it a base? OH.
OH.
Ah, cool. And what's the charge on OH?
-1.
-1.
Oh,
So I got a copper +2. How many OHs do I need?
2.
Ah, there we go. So that's the base.
0 H.
So if I take these two guys and mix them together, I'm going to get copper sulfate. Right? Do you see that?
Sure.
So I'm going to add an OH to a positive one. I'm going to add an H to the negative one. That's how I'm going to do it.
It's 2 waters.
Okay. Now, here's how you figure out what the salt's going to be. Is the acid or base stronger?
The acid.
Is the acid or base stronger?
the acid.
This one is, right?
Yeah.
Well, then the salt's acidic.
Hmm.
If you want a rationale behind that, H2SO4 is a strong acid, right? So it completely breaks up. So when I add sulfate to that solution, none of it turns into sulfuric acid because it's strong. It stays broken up. So the H doesn't move. On the other hand, copper hydroxide is a weak base. And so when you add copper ions to the solution, it pulls OHs out of the solution to turn them into copper hydroxide. And so I have more H's than OHs, i.e. that's the definition of an acidic solution, right? Because I didn't change the H's, but I pulled a bunch of OHs out, so I got too many H's, that's acidic. Does that make sense?
Yeah.
You see where I'm coming on that? Make sense? You got it? Got it? No? You don't have it? Need more? Let's try another one. Let's do that one. And that one. And there we go. Are those salts acidic, basic, or neutral? I dropped those into water. They're going to be acidic, they're going to be basic, they're going to be neutral.
Let's find out.
So ask yourself, what acid and base would I make out of these two guys?
I think it's neutral.
Start here. So we're going to add an OH to the positive and an H to the negative one, right? So potassium hydroxide, strong base, weak base.
Strong.
KOH, strong base.
Yeah.
HNO3, strong acid, weak acid.
Strong acid.
Strong. Which is stronger? Which is bigger, infinity or infinity? Neither?
Yeah. It's neutral.
Potassium's like, I don't want your hydroxide. Nitrate's like, I don't want your hydrogen. Fine, water, keep whatever you got. I don't care. I don't want anything to do with it. Neither one of them is strong enough to pull hydrogens or hydroxides out of the solution. So the solution stays the same. Doesn't change. Okay? Calcium cyanide. Calcium, strong acid, weak acid. Base. Strong base, weak base.
Strong base.
Strong base. Cyanide, strong acid, weak acid.
Weak acid.
Weak acid. Okay, what's this salt? Which one's stronger, the base or the acid?
The base.
The base. So it's basic. How about this? Cobalt hydroxide. Strong base, weak base.
Weak base.
Weak base. HI. That's a base. Strong acid. Yeah, so acidic. See how it works?
Yeah.
Next Friday, you're almost certainly going to get a problem that's going to be A, B, C, D. Here are 4 compounds. When you dissolve them in water, are they acidic, basic, or neutral? And you should be able to fly through those and get all the points by just going acidic, basic, neutral. That's all you gotta do. Okay? So that'd be some free ones there, if you know what's going on.
I guess it's neutral.
Let's do one, what is what? Is that right? Is it next Friday? Oh, Friday after, well, whatever.
Oh my gosh, you really stressed me
Am I making you
out.
nervous?
I was hoping it was.
I was like, I mean, it probably.
I've got a girl from New Zealand in the other class who has to go back to New Zealand for surgery, and I'm giving her the test. That's what it was. Okay, but you know, if you guys want to, you want to take this week early.
No, thank you.
He's saying he wants it early.
Wait, can I?
All right. Okay. Well, think of it this way. Think of it as it was good for your heart, right? Get a little adrenaline, knock the plaques off your arteries, all that kind of
It
stuff.
actually decreased my heart rate
Okay, there you go.
to 100.
Increasing your heart rate is always good for it, right? Okay. So,
Yeah. But
all right. Do you see how to do that? Does it make sense? Okay, cool. All right. Okay.
What do we wish there?
weak acid is equal to strong acids. Strong base. How many do you get?
What's the pH of a solution that is made up of 0.15 molar ammonia and 0.20 molar ammonium chloride?
Let's write these down.
Okay, you guys want to help me out here? Ammonia, it has what formula?
NH3.
NH3, and ammonium,
NH4.
NH4 plus. Okay.
Yeah. Do we need a KB?
Oh yeah, you probably do.
This is how that goes, right?
Thank you.
That'll be handy. Better, guys?
I don't think we can collect X. In fact, I'm pretty certain we can't.
This is reacting to water. That's the reaction. Didn't do it.
And it's NH4, so
That's a salt.
that's nasty. I appreciate you. This is 4.7.
Do not fall into the trap of trying to react ammonia and ammonium chloride. Ammonium chloride is a salt that is added to the acid-base reaction. But it's reacting with water because it's when you put ammonia in water, that's
Oh, but see how it's doing that.
And then
Oh, does it all break up?
Yeah.
Yeah. NH4 and Cl don't exist to it.
no, that one is just that's a salt. So it breaks it.
it's with zero. Zero had it. Yeah, we just have to do it.
Burn.
That's not an ascorbic base, it's a salt.
Frankly, burn.
I'm always.
Pretty sure we've got to put that.
Okay, so this is what I'm seeing a lot of. NH3 plus H2O goes to NH4 plus OH minus.
Yeah.
Okay?
Yeah.
That's what y'all should have got for the reaction. That's what ammonia does when you react. Okay? So, let's see what we got here. How much of this do I start with? 0.15, right? How much ammonium do I start with?
0.2.
0.2. Because notice, conjugate base of a strong acid. So it totally breaks up. It's the weakest possible there is. It has no bond at all, right? Real easy to break it up. So this would be a strong electrolyte. I guess I didn't officially mention this, so I'll go ahead and do it. But any of the salts of the strong acids are going to be strong electrolytes. Any of the salts of the strong bases are going to be strong electrolytes because they totally break up, right? All right. I will say it's my typical practice to actually mention that something is a strong electrolyte in the problems on the test, just so you don't have to remember if you forgot that sulfuric acid was a strong acid, you don't miss the problem. Okay, so I don't know, can we do it from there?
Yeah? No. Yeah, it's pretty sure you got a quadratic.
Nasty.
This was fairly tedious. It's not a distributed.
This is a strong electrolyte, that completely breaks up.
Right.
So that one, so these need to be this.
That's not KB. Oh, PKB. I think you actually can.
Yeah.
I goofed. I didn't see that.
What did you do?
I used
We're gonna neglect
You
that.
always start with water on the
Well,
reactants.
I'm gonna try to do all that.
Yeah, because I'm putting it in water. It's always, the reactions are what I have. I take ammonia and I put it in water. Right here. See, I react that with water. I react that with water.
Yeah, this is X equals. That is.
I'm not gonna say I didn't do it, but if I did it, it was a mistake. Oh, let's see what we got here. So we don't start with any of that. So we got minus x, we got x, we got x, right? So 10 to the minus 4.74 is equal to x times 0.2 plus x over 0.15 minus x. Let's try to drop those x's. So if x is really small relative to 0.15, that's the smaller of those two. At that point, it should be pretty easy. So I don't know what x is. Whatever we get, we get.
What do you get?
Number? Got a number?
Oh, X 1.36 times 10 to the negative 50.
Anybody else get that? Cool. Okay, there we go. And what's this? What does x stand for? It's the OH.
Yeah.
Always got to remember to go back and say, what does X actually stand for? Because it's, I can tell you on the next test, some of you are going to go, hey, there's X. Take the negative log of it, and that's my pH.
No.
Nope, that's my POH, because that's OH, not H, right? Okay, so my POH is
9.1.
4.97, 87. And so my pH would be what, 9.13? Okay. Now think about that for a second, and it should totally make sense to you. Normally, my pH would be, I don't know, what if it was just 0.15? Just do x squared over 0.15 equals 4 point. In other words, if this was 0, what would I get? So 10 to the minus 4.74 equals x squared over 0.15, right? So what would x be now? What'd you get? I can't hear you. Let me see, Brian. 10 to the minus 4.74 times 0.15.
0.0017.
0017. So 1.7 times 10 to the minus third?
Yeah.
1.7 times 10 to the minus third. So my POH would be like 2.8 or something? 2.8?
Yeah.
Okay. So 2.8, so my pH would be
11.2.
11.2, right? Okay, look, this is what that ammonia would be. What is this right here? What is that in Bronsted-Lowry terminology? What is that?
Conjugate acid.
It's an acid, right? Oh, look, I added acid and the pH went down.
Oh, yeah, that makes
Yeah,
sense.
that tracks.
Yeah, I have a base, I add acid to it, the pH should go down,
You're so
right?
Yeah.
So I mean, it fits what it ought to do. Does it make sense?
Yeah.
Okay, and then we can use that number to quantify how much it is, but just from looking at the equation, you should say, if I add, okay, let's say that I added 0.5 molar ammonium chloride. What would you expect to have happen to the pH? Don't give me a number, just tell me what you would expect to happen. Direction-wise, what should happen?
0.5 molar.
0.5 molar ammonium chloride. So now that's 0.5. What would you expect to happen?
pH go down.
The pH should go down more, right?
Yeah.
And you're right. That's exactly what it does. Cool. Have a good weekend, guys.
I understand.
What mountains did you live on?
I don't know.
No,
It's really bothering me. Look that
I'm
up.
not looking it up.
Give me a moment.